Hi, you're currently watching the recorded version of the Miami University's Physics 121 Energy Environment recorded lecture, first recorded lecture specifically. So one of the things that I want to do right now, of course, you're not seeing any slides. I wanted to get some of the logistics out of the way since this is supposed to be the first recording. If you're watching through any of these and you're curious or you're in the class currently, needed some other information, wanted to hear it a second time, or if you just had to miss that particular day, it's not a big deal. All the material that I'm planning on presenting in lecture will be included here just as well. But one of the things that I'm specifically not going to do is talk very much about assignments or do some of the regular announcements in class activities that we would have typically. This is primarily going to be focused on just delivering the content in some way or another. I'll talk about a few of those things at the beginning here, but for the most part, from now on, after all of these videos, it's going to be primarily just focused on the content. If you want any other information about assignments, what you should be doing for those things, that's better left looking through announcements, looking through the due dates on Canvas, and if anything comes up that you're not sure of, sending me an email. So, with that said, one of the things that we might run into a little bit here is that I'm going to be recording these around the time that I do lectures, but not necessarily on pace. I'm going to try to organize these in such a way that it's easy to figure out which one is next. All the details I'll talk about if we're covering things. Usually I'll probably spend 2 videos working through one single set of slides as we would normally be doing in the lecture class. So for example, this is 1-1 and you'll see the second half of this lecture in 1-2 with the next one being 2-1. There's a possibility that some of the lecture material doesn't exactly align with what I'm doing recording here. Just because if these aren't created at exactly the same time, one might get a little bit ahead or behind or the other. But I would say generally for the most part, that shouldn't be a big issue, especially because the bulk of material is going to line up quite well. If you ever find yourself in that circumstance, you're working on something, you realize that it's not something that was said in the video, take a look at the next one. Or, likewise, if you're in the lecture and realizing that something's not quite what you had seen before in these videos. But anyways, I think that covers all of my bases for now. How's about let's get ourselves into the actual lecture. So, typically, I'm going to be just working through this lecture, talking about these things with my face up here in the little corner. And a lot of these details you might be noticing about the course, those are things that we're just going to kind of skip over for now. If you'd like, you're welcome to read those through on your own time. Let's go ahead and talk about really where all of this stuff is happening in the first place. Right? We're talking about the Earth. Generally speaking, if you want a history, how did we actually get here? The current theory that we're running with is that the Big Bang spews a bunch of hydrogen and light into the universe. It started as this super high energy plasma to the point that calling it hydrogen's not exactly accurate. It's a lot more similar to what's going on in the sun, where what we are calling hydrogen is really just free-floating protons. It's simply way too energetic at that point for anything to form into a regular atom as you would traditionally think about it. Instead, all of the particles are constantly just buzzing around back and forth, colliding into each other. Nothing's able to really stabilize quite yet, and it's spewing out all over into the universe. A lot of that hydrogen is going to start condensing. Right, naturally, through gravity, those things with some sort of mass to them will start to condense in certain locations. And this is happening pretty randomly throughout the entire universe, right? If you think about what star clusters look like nowadays or how galaxies are formed nowadays, this is just kind of random happenstance. Some areas, because of this random distribution of hydrogen, you've got really thick clumps, and that's what form our galaxies. In between those, you've got scattered little bits of space dust, which is, again, mostly just hydrogen, but it's randomly distributed, which means you've got some pockets that are really dense, some pockets that are a little bit less dense, and they're beginning to form a lot of these galaxies. Everything heavier than hydrogen is generally going to be formed in stars. So inside of a star, we start with regular single protons, hydrogen, again, still a plasma, so not really, but kind of like hydrogen. But the first step that happens here is that you've got all of this hydrogen, all of these protons that are packed together extremely tight, right? There's an intense gravitational force keeping all of them together because normally hydrogen doesn't want to be that close. But because there's enough of it, there's such a strong gravitational pull at that point that these protons are bumping up against each other nearly constantly. And occasionally what will happen is that there's just enough energy between those two of them that they clump together and they stick for a minute. And when they stick for a minute, they're really unhappy about that. Generally, protons don't want to be right next to protons. So what happens is you see this decay. One of the protons becomes a neutron instead. And now you get a material that we can call heavy hydrogen or deuterium. It is a proton and a neutron, so still chemically hydrogen, but a little bit bigger than hydrogen normally is. From there, sometimes you'll have a third proton come in and do the exact same thing as the first two, where that extra proton becomes another neutron. And then you've got a material called tritium. Sometimes that works, sometimes it is just two deuterium molecules, not molecules, but atoms combining together into one. Point being, what you eventually get to is helium. And helium is a lot of where our sun currently is going, right? So that's the next step up the ladder when you're talking about building atoms bigger and bigger. And it actually turns out that this process continues. When you start to combine these individual particles together into larger and larger atoms, into larger and larger particles, each step along the way releases energy, right? That's why the sun is up there burning in the sky. All of that light that we're feeling, if you think about how really incredible that is, imagine how close you have to stand to a bonfire to start to feel its heat. Now imagine how far we are away from the sun currently, and you step outside and you feel that same amount of heat. There's a huge amount of energy being released by the sun constantly. And the source of all of that energy is really these individual particles combining into something just a little bit larger and releasing massive amounts of energy in doing so. And it turns out that this process actually continues. So right now, comparing with what our sun is going through, right, it's kind of in the middle of its life. It's still got a lot of hydrogen left, but a significant amount of helium is formed, right? And maybe even some other heavier elements. If you're going just a little bit up from there, you start to get to things like lithium, carbon, nitrogen, these heavier and heavier particles. And it's just more protons, really energetic, are getting close enough that they combine together. They fuse into one single particle. And that continues all the way up until iron. Iron is the very last step where energy is continued to be released. Because if you think about this, some of the knowledge that you might already have about some of these different energy systems, right, you maybe know about things like uranium and how energy is extracted from radioactive uranium, right? You've heard of splitting the atom before. When a uranium atom is split, it releases energy. That's because it's after that hump. It's after iron. So everything heavier than iron, it takes more energy to combine it together. And if you split that atom, that energy is released back. If you're looking at something like hydrogen and helium, though, combining them, making them a larger particle is actually what gives away the energy. And it takes energy to split them back apart again. So we'll see this in a couple different circumstances, especially by the time we get to nuclear power, really the different processes we're looking at here. But what this means is that for the most part, regular stars only form up to iron. So all of the elements up to iron can form, interact in stars. Everything heavier than that is only formed in a supernova explosion. So when a very, very high energy star explodes, when it reaches the end of its life, there is this incredible amount of energy released. There is a sudden density increase in the middle of it. There's energy released all the way outside of it. And these extreme scenarios are exactly the places where you can start to form very, very heavy elements, right? You've got just so much energy, so much force, so much momentum in each of these particles that you start to form these really, really large pieces, like our uraniums, like gold, like silver, like even some of the more unique ones, like indium. All of those are actually formed in supernova. So right now, if you're wearing a piece of jewelry, chances are that was actually formed millions of years ago inside an exploding star, which is, I think, a fun little tidbit to kind of carry around with you. So when this happens for a very long period of time, right, because the universe is not a particularly new place to be, but when this happens over a course of millions and millions of years, you go through the entire lifetime of stars. Stars form all of these elements, they explode, they spit these elements out in the vast universe, and then those atoms go off and do other things. Other things like forming Earth. Earth is not actually composed of hydrogen like these other stars. Actually, what it is consisting of is these heavier elements. Right, we've got a lot of silicon, we've got a lot of carbon, we've got a lot of oxygen, we've got a lot of nitrogen, we've got all of these different things that are forming up the bulk of the Earth. And then, again, there's plenty of hydrogen left in the universe, so that forms things like the sun. But all of the planets in our solar system are consisting of those heavier elements, whereas the very, very light space dust, hydrogen and helium, is still forming to create more stars. So, talking about this big heavy ball that we live on. Technically speaking, there are 3 different layers of Earth, and we kind of have to think about all 3 of them. But for the most part, we're going to focus on the surface of Earth because that's where everything is happening, right? There might be some interesting things going on in those deeper layers, the mole people, the spinning of tectonic plates, whatever there might be. But the surface is where we are. The surface is where our geothermal plants are. It's where all of our stuff is. We haven't really broken through the crust very much, so it's most of what we're going to be focusing on. But one of the things that you might know on this one is that the Earth does indeed have a molten core, right? And then because that core is very, very warm, the outside has cooled. It naturally radiates heat away back into the universe, but the interior has, well, a pretty thick layer of insulation around it, right? All of these miles of rock are stopping that heat from escaping. And so eventually, very, 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 very slowly, that heat does seep out to the surface of Earth, but for the most part, it's pretty well contained inside of the Earth, where a lot of the heavier elements are simply because they're more dense. Right, the lighter elements primarily float to the top, but when I say float, right, this is happening over a process of thousands of years because rock doesn't really flow super quickly. But we generally have the lighter elements, but that distinction is not really too significant for what we're going to be considering here. For the most part, we are thinking about the surface. So, early in the Earth's existence, there was a whole lot of nitrogen, there was a whole lot of carbon dioxide, right? That was primarily what was making up our atmosphere. There were other things as well, of course. There are other types of gases that were existing at the time, but nitrogen and carbon dioxide were 2 very, very big ones for 2 reasons. For one, nitrogen, once it bonds to other nitrogen, so nitrogen gas, is very difficult to break the bonds. If you remember anything from a previous chemistry course, you might remember that there are 3 valence electrons between those 2 atoms. That's a very strong bond. They're not very willing to break that bond. It takes a lot of energy to do so. So nitrogen will primarily want to continue being nitrogen. Carbon dioxide, on the other hand, a little bit of a different story. But what it is that oxygen is very reactive. It's incredibly reactive. It reacts with just about anything that it possibly can. If you're ever hearing about things like antioxidants, right, that is anti-oxygen, things that when oxygen mixes with them, it interacts and changes what that chemical composition is. So oxygen being this more prevalent thing really couldn't happen at a time like this. There wasn't something providing the oxygen. Anything that was potentially reactive with oxygen was reacting to the oxygen. And that's what all this carbon dioxide was, right? Carbon dioxide naturally forms when you're doing other things like burning. There's a lot of carbon in the universe. It will naturally form through that process. If you're looking at what life on Earth looked like at the time, we were still a lot of bacteria, right? These single-cell organisms, and a lot of them are not necessarily interacting with oxygen at this point. A lot of them are depending on geothermal energy or certain chemical releases from deeper in the Earth's crust to actually get that energy to sustain them and to reproduce to the next generation. Later, after life had been around for quite some time, plants started to develop, and I wouldn't even necessarily call them plants yet. These were more on the order of phytoplankton, individual cell organisms, or sometimes a few multi-cell organisms that were able to interact with that sunlight, that high energy light coming from the sun, and were able to utilize that and some other chemicals in the atmosphere or dissolved in the water that they were in to start through the process of photosynthesis, right, that we know of that plants use today. So what happened to this carbon dioxide? For one, a lot of it got dissolved into the ocean. A lot of it was what in a process that we call weathering, it reacts with rocks that are exposed on Earth's surface, and it kind of forms like a very thin little crust. Think about like how silver tarnishes. Something just like that, where it naturally is reacting with some of the oxygen or some of the carbon dioxide, and it forms some sort of film on those surfaces. So between all of these things, early plants, weathering, dissolving in the ocean, we start to see the increase in oxygen gas. And this was not super appealing to a lot of organisms at the time. And in fact, some organisms still, if you introduce them to just regular oxygen gas, they have a problem. Because again, oxygen's really reactive. Right, there's a reason why you're not supposed to smoke anytime somebody is on some sort of actual oxygen support, because pure oxygen is that's condensing, refining that very reactive thing that already makes up a significant portion of our atmosphere. It is more than happy to interact with anything, right? You'll notice this in rust, in things tarnishing, all sorts of different things where this reaction happens over time. Oxygen is being involved, right? Burning requires oxygen. If you're thinking about what actually sends rockets into space, they've got a tank of liquid oxygen that they're burning, and because it's so incredibly reactive and releases so much energy, that's what actually sends the rocket up into space. So what I'm really getting at here is that this oxygen was a big deal. Organisms at first didn't know how to deal with it. It was dangerous for them. But these plants that were starting to produce it opened the way for a lot of these other organisms to form that could actually use it in what we call aerobic respiration. And aerobic respiration is basically utilizing this oxygen gas to form new chemical bonds that release a lot of energy. And that's just not something that could be done before. Looking at some of these other organisms, right, they didn't rely on this oxygen. They couldn't release this same amount of energy in one single process, so they were limited in size. But with oxygen being plentiful, well, you could start to create much larger organisms that didn't require nearly the same amount just gathering the energy, could focus a little bit more on getting the most out of whatever they were consuming, because oxygen was there to help release even more energy. So it's this stored chemical energy that they have that oxygen is really utilized for, right? If I'm thinking about what's going on with my oxygen right now, I've eaten a meal recently. That's not doing anything yet. But over time, my body's going to break that down into individual carbohydrates and other things that are going to supply my cells with energy. Oxygen is going to come in through my blood, through the hemoglobin, interact with those individual molecules that my body has broken down, and release huge amounts of energy, relatively speaking, of course, but huge amounts of energy that my cells are going to be able to use to do all these things, like sitting here waving my arms around and talking. So, talking about this, because I know this is going to come up later, we think about what was the temperature looking like, right? I think everybody's mind nowadays goes a little bit to considering temperature when you're thinking about something like carbon dioxide, right? That gets brought up. We think greenhouse gases. We start to think about climate change and everything that comes with that. So this is a little bit of a rough graph based on what we expect the temperatures were in a lot of these places. And I say expect, and it's really a little bit more exact than that. Two things you might notice. First of all, yes, when there was a lot more carbon dioxide, the Earth was indeed warmer. We have some other changes that have occurred since then, right? As life on Earth has been changing, as the chemical compositions of our crust and atmosphere have changed, those have all been pretty major factors, in addition to other things like volcanic eruptions can have significant long-lasting impacts on the temperature of the Earth. But the other thing you might notice is a little bit more about the graph itself. You might notice that we've got, for lack of a better way to describe it, it's really just kind of rounded out, right? Everything's pretty well rounded out in these older times, whereas you get more and more close to the present and you start to notice that it's a lot more spiky in nature. And this is for a couple reasons, right? Largely, one of them is that, realistically, especially if you're talking the last 100 years, we've been able to directly measure the temperature. We've got thermometers nowadays. We can record the temperature, and comparing even a few hundred years ago or 100 years ago to today, how we're able to record that temperature has drastically changed in the accuracy that we're able to achieve this, in surely the number of recordings that we're able to make, in the variety of locations that we're able to take these temperatures. So in looking at it like that, of course, more recent times we're expecting a more accurate representation, because we can do this not even day by day, we can do this second by second, looking at the temperature in all of these locations over the world, where 100 years ago, that simply wasn't possible. But even then, this spikiness, right, 1.8 million years ago, that's a little bit of a different story. So what's happening here? Well, it's really in how we're able to collect the data. The older something is, the more difficult it is to really distinguish. For a couple different reasons. For one, because of course, history stacks on top of older history. Right? We demolish buildings, we build on top of them. The same thing goes on with snow and land and structures that were naturally formed. Volcanic eruptions slowly weathered down. A lot of details like that. So for one, you start to lose a lot of the data. The number of places that you can really get good samples from to understand what was going on at this time period is a lot more difficult to do. There's just fewer samples in the first place. Two, how we are able to date a lot of these readings is also quite different. If we're talking about something like carbon dating, that's good for a few thousand years. But if you want to look back past that, millions or billions of years ago, you have to be a little bit more careful. When you're dating things like that, you have to rely on different sets of substances or different time events that you can notice, right? If you notice a layer of ash, then you know that this must have been some sort of significant volcanic eruption. Some of these dating techniques that we have, what ends up happening is that we begin to bin up more and more data into a single time period. So what am I saying with that? Let's say we're looking from the span of 1 billion to 2 billion years ago. It's going to be difficult for us to distinguish 1.5 billion from 1.8 billion. But if we're looking at modern day history, it's very easy to distinguish 1 day from 2 day, right? Or even when we're going to the span of 1,000 years, it's very easy to distinguish 1,000 years versus 1,500 years. We could sometimes even distinguish it down further than that into individual years. But the bin that you have to put all of this data into starts to get wider and wider and wider the further back you go. So that's a big part of the reason why we see such drastic changes more recently, because we're a lot more accurate. We can much more clearly distinguish when this actually happened. We're binning at this point maybe 100 years together rather than a couple million. But at the end of the day, I bring this up and I said that we really couldn't call this an expectation of what the temperature was. We are very confident in a lot of these numbers. There are more things that we'll get into when we actually talk about the climate change section. That is a little bit later on in this course. But we do have a lot of confidence in data like this. This is not just kind of guessed, pulled from thin air. This is multiple different techniques from multiple different locations, all brought together to be able to form a single data point. So I really don't want to diminish the effort that it takes to produce a graph like this and the amount of work it takes to get this to a point of certainty where we can begin to present it like this. But anyways, that's probably enough about the history of Earth. Let's talk a little bit more about what's going on today. Right now, as the Earth exists, the atmosphere that we think about is broken up into these, I'll call them 5 layers, but that's not really true. The exosphere is not actually a layer of the atmosphere, right? That is kind of an Earth-centric name that we call outer space. Exosphere is anything out of the atmosphere, in outer space. So I'm going to really say that the Earth's atmosphere is busted up into 4 different layers, and you can see a little bit of what's going on in each of these layers. The part that we're primarily going to focus on is going to be the troposphere, right? Probably unsurprisingly, because that's where we are. That's where everything is that we care about. Of course, there are things happening in the upper layers. We'll make some mention of them, right? The ozone layer kind of staring at me right in the middle of the page there. But for the most part, we're going to entirely focus on what's going on in the troposphere. We'll make mention of the other layers from time to time, but we know that's where we are. That's what we care about. There's a couple different things that you can look at in comparison between some of these. These are just some of the details that we see piece by piece what each layer has for us. The troposphere, the one that we live in, has the majority of water vapor in the atmosphere. It's got all the dust, it's got all the clouds, it's got Superman, most of the carbon dioxide, it's got a little bit of everything, right? This is where we exist for a reason. Lots of pressure, pretty high temperature, all the good stuff to interact. The stratosphere is very little water vapor, a lot of ozone though. For the most part, looking at some of these other things, we're not particularly interested in these, especially the mesosphere, the thermosphere. They're just not interesting things for us, right? There are some cool things going on in there, of course, right? In the thermosphere, we've got stuff like the northern lights, which is actually the sun spitting out really high energy, dangerous particles. And our atmosphere is kind of eating away at that in those upper layers. Beyond the point of what we're focused on now, right? Very cool thing. There's a lot of neat stuff going on in each of these layers, but for the most part, a little bit outside of the scope of what we're going to consider. Here's just a zoomed in view of what's going on with these things. Now, one of the questions is what's going on with this temperature and energy? You can begin to think about this in a sense of, okay, so we see how these temperatures have changed, but what's ultimately responsible for that? Why does it change? Well, how do you boil water? It feels like a little bit of a simplified view, I know, but the only way to change the temperature of something is to change the amount of energy that it has. So for the Earth to warm up, more energy has to be collected than is given away. And the Earth does give away energy. Anything that has temperature, and that is everything, anything that has temperature is constantly radiating away energy. That's just a natural part of what it means to have energy and to have temperature in the first place. And you might notice some fun things in your life for these. So for one, the temperature that you are is a very significant part of what you are radiating as far as it goes. I'll get into some of these details a little bit later, but I do want to mention this right now. So the sun is very toasty, around 5,700 Kelvin, which, I mean, at that point, the distinction, 5,500 Celsius, whatever it may be, it's hot. Right? That's what we're getting at. When something as hot as the sun is radiating away light, it is so energy intensive that a lot of the light that it radiates is visible light. Actually, if you wanted to break this up, about 40% of that light is visible, about 40% of that is in like microwave infrared territory, and about 20% of that is in the UV spectrum. And the UV spectrum is why you need to wear sunscreen outside. right? That's the type of light that's actually quite dangerous, very, very high energy per photon, which means that it can kind of mess up what's going on with cells. It's also what breaks down a lot of the different compounds that are found in the atmosphere. So high energy, a lot of things interact with it, right? It's a little bit rough to be around, but it spits out a lot of visible light, and that's what we see. Right now, you are emitting some light, but it's light coming out in the infrared spectrum. Our eyes are not sensitive to that part of the light spectrum. It just passes right on by. It doesn't actually see anything. But you are currently radiating this away. And I think one of the fun things that you can do to really see this, that as something gets hotter, it radiates more energy, and that energy becomes more and more visible, is turn off all the lights and turn on a stove burner. Right, now if you have a gas stove, this doesn't work. Sorry. But if you have an electric burner, this is perfect, because what you'll see is right at the very beginning, the room is dark, you don't see anything. You turn on the burner and you start to watch that, and what you'll start to notice is that it ever so faintly starts to glow red. You probably don't notice this when the lights are on when you're cooking in the kitchen regularly, right? Because the amount of light that it actually puts out in the visible spectrum is pretty low. And a lot of what that isn't even that there's not that much visible light. There is a little bit of visible light, but the faint red that you see when the lights are all off is actually there's not a steep cutoff point for that infrared light. So just in the near infrared is what we call it, where our eyes can't quite see it. There's still a little bit of a curve there that our eyes can't pick that up. And a lot of the light that thing is putting out is right in that range. So with that whole lot of light and a little bit of visible, we can start to pick that up when there's not a lot of other interference from kitchen lights, from other things going on at the same time. But you'll see this because as it becomes hotter and hotter and hotter, it will go from completely dark to a glowing red that is very clear to see by the time it's at maximum heat. Now, don't keep doing this for a very long period of time, right? It could be damaging for the burners, but I think it's a very fun experiment to really see what I mean when I'm saying that everything is radiating heat, everything is radiating light, but we can't always see that. It's not always apparent to our eyes. But all of this was a huge tangent away from the original point that I wanted to make of energy has to come from somewhere, right? There has to be a transfer of energy one way or the other. The Earth is constantly spitting out energy and is constantly taking in energy, right? And the vast, vast, vast majority of that energy is coming from the sun. Anytime there is a change of energy or a difference between these two values, that's when we start to see a change of temperature. So it's not only that we could increase the amount of energy coming in, but we could also decrease the amount that we lose. And when you're talking about something like climate change or the greenhouse gas, it's that second part that's actually what's happening here. So what do I mean when I say the vast majority of energy the Earth receives is coming from the sun? I mean the vast majority, 99.98%. A significant amount of the energy, right? The overwhelming majority of light, or the overwhelming amount of energy is coming from sunlight. There's a really tiny amount coming from just the natural geothermal flow. And when I say geothermal flow, not even all of that is actually coming from our molten core. Only a small portion of that is actually coming from the molten core. The rest of our Earth's interior energy is actually radioactive compounds in Earth that are slowly decaying and giving off energy when they do so. So there's so little energy actually coming out of the center of the Earth. It is primarily these other sources that we see. But anyways, when you start to see some sort of difference between these two values, that's when you start to see some sort of temperature change. And that's something that we're going to have to talk about in a little bit more detail later on in the course. I don't want to spoil anything too much yet. I don't want to get into too heavy detail. I know I've talked about this way too long already, but I don't want to get into any sort of crazy details yet without having the chance to actually go into more about how we study this, how we know these things, a little bit more about how these systems interact. So that'll be coming up later, again, later on in the course. Anyways, human population and the rate of growth for a lot of these things, right? When we're thinking about environment and energy, the energy part didn't really matter until people were there, right? I mean, I guess it did, but yeah, do we really put that much thought into what the quality of life of a dinosaur was? Not really. We're mostly focused on the people. So this is an important thing, though, because all of these people that exist on Earth require energy. In a lot of different ways, too, right? Not just through electricity, not just through fuel for a vehicle, but also things like food, also things like medicine, like commercialization. When you're talking about industry or the jobs that they do, energy is required for all of these different things. And the source of that energy could be something as much as an apple, to gasoline, to an electric power distribution grid, any of those things. All of these people require energy in some way or another to survive, to continue living. So when the number of people increases, so too does the demand for this energy. And this has a little bit of an interesting trend with it as well. If you're looking at the world population, this is a nearly exponential growth that we see, right? As more people exist, as the life expectancy increases, all of those things, we start to see more and more people on the planet at once. That's not to say that the growth rate has been constant, right? Kind of an interesting detail here. If you look at the past few decades, the growth rate, so that is basically saying if we have 100 people, then in the next year or 10 years, we're going to have now 101.6, right? Scale this up to billions of people rather than just 100, but that's the idea that we're going with here. The rate of growth relative to the current population. So it's not that just that we're adding 10 people every single time, but we're adding, 10% based on what we've already got. Not 10%, more like ones and twos, but that's what I'm trying to get at here. So the growth rate has actually declined in recent decades, and that's for a couple of different reasons. I don't really want to get too much into the semantics on that point, but if you are interested in that a little bit more, this also varies very much country by country. But globally, that growth rate has started to go down a little bit, but it is still growing, right? It is not declining the other way. That slope is still going up. So we've got a poll for things like in-class stuff, discussion. Again, if you've got a little bit of graph literacy, I want you to spend a little bit of time and think about this one. Just consider some of these thoughts. So, talking about people need energy. This is the spot where I really want to kind of put it into perspective. So one of our books uses this description of energy servants, which I know that there can be some things surrounding this, but let's talk about this. So I'm not going to do this because I'm on camera, I'm recording, but in class, I did do this a little bit, and I think it's a good thing to do, to try it out for a little bit. I really do mean this. If you're sitting there, pause the video for a minute, try this out. What I want you to do are just some basic squats. Right? No weights or anything else like that, just kind of squatting in place. You can use something to hang on to make sure that you don't tip, because please don't hurt yourself. But either doing this or jumping jacks or something that just gets you breathing a little bit more than just through your nose, right? Maybe a tiny little bit of a tinge of sweat or something else like that, but a little bit of breathing through your mouth, just enough that you're starting to feel that you are exerting yourself. So pause the video for a minute, go try that, please. And hopefully you're coming back from that pausing. So what you have just done is output about 100 watts, particularly if you were squatting. That is a perfect example, as we'll talk about quite soon here. I know many people don't use these anymore, but especially in cheap houses, if you're looking for the cheapest possible light bulbs, that's about a medium brightness incandescent light bulb. One single medium brightness incandescent light bulb. And what I've got in my room with me right now would fit for this amount of light in the room currently is 2 light bulbs. Now, I'm using LED light bulbs, so it kind of breaks this description a little bit, but incandescent light bulbs were the whole thing that we used for like 100 years. So this description, I think, still works pretty well. modern jumps in this efficiency have ruined a lot of my examples. But basically what that's getting at is that just for lighting this room, for me to be able to record this video, would require 2 people constantly doing squats or pulling on a rope or doing something else like that to generate the energy to run those light bulbs. Now, if you're thinking about how much energy does my desktop use, that's on the order of 500 or 600 watts sometimes. So now that's 5 or 6 people right here, not a camera crew or anything else like that, but 500 or 600 people pulling on ropes, spinning generators, hand cranks, whatever, just to generate the energy required to run this operation right here. And that's an interesting thing. You start to think about that, and you start to consider what it actually takes. And I think this is a really good place to really bring up this idea of what the typical occupation of people has been for a long time in human history. If you think of medieval peasants, we should probably know, made up the large majority of people in those medieval eras, right? In those medieval countries specifically. But point being, the percentage of people in that position, and the majority of them, farmers. Farmers or manual laborers all working those individual jobs. And now you compare that to today's day and age, where instead of having the overwhelming majority of people be farmers, I know a handful of farmers personally. How many do you know? There aren't that many farmers anymore, not at least in these developed countries. In more developing countries, you see that shift a little bit more, right? There's still a significant portion of the population that is just farming, trying to supply food for everyone. That's another form of energy, right? It's not an energy that we put into a vehicle. It's not an energy that actually runs our computer, unless we've got 5 or 6 people turning hand cranks, but it is still energy. And that's a lot of what fed into the Industrial Revolution. This idea that suddenly we had this fuel source that could do the work of 5 or 10 or 100 or 1,000 people with one device that one single person could operate. Now, we didn't need nearly as many people to supply that food because we had 100 people in this machine that we could use. So a lot of developments like that have really allowed us to do many of the things, research and all of these unique jobs that we have. The modern quality of life is very much determined by this idea that we can use more energy than any one single person can provide. Not one single person is really required anymore. If you're thinking about yourself, myself, somebody working in a lot of these developing countries, not developing, in these developed countries, we're looking at circumstances where you are not necessarily required to contribute your 100 watts. Or if you do, it is assisted by all of these other things surrounding us. And that frees up our time. That frees up our time, that frees up our energy, that frees up our effort to be able to do other things. But this is why I think it's such a good example to consider. This is why it is so incredibly difficult to diverge ourselves away from the modern quality of life features. You have to go back to becoming a full-time farmer just to support and survive. That's all you can do at that point. It is with the advent of all of these different energy sources that we can extract this energy that we're able to go past that. So, some values here, right, to consider how some of these things all fit together. When I'm talking about 100 watts, I do want to specify that this is not energy, this is power. And power and energy are very closely related. I don't want to split hairs too much on that one, but power is the rate of energy. So the most common unit that we use for energy, at least in physics, is oftentimes joules. So joules are just a common, simple unit. The easiest way to consider this is something along the lines of, if you take some 1 kilogram object, you lift it up a meter, that's about 10 joules. So you doing those squats, however many kilograms you weigh, about that half meter that your center of gravity rises, right? That's how many joules that you're putting into that pretty quickly there. But when we're talking about useful work that a human can do, it's about 100 watts. So if you wanted 100 joules of energy, you've got to be doing that for, 1 second, or if you wanted more than that, for those consecutive seconds to actually operate. If you think about how long you might spend on a laptop that's using about 100 watts, or typically 90 watts is the limit, then you're going to have to be pulling that rope, turning that hand gear, doing those jumping jacks for those 4 hours just to supply the power for that single device. To put this into a more human perspective, the value that we typically call in America a calorie, right? So if you're looking on the back of your food box or anything else like that, you might see a value that says something 90 calories, 120 calories. That is not actually what a calorie is. That is a kilocalorie. I, for the life of me, don't understand why we have done this. But technically speaking, a kilocalorie is the thing that in America today we typically just call a calorie. And the difference is a calorie has a lowercase c, a kilocalorie has an uppercase c, and if you say it, there is no obvious distinction between the two other than the fact that the kilocalorie is what we usually refer to. Mess that it is, it's what we have to work with. But point being, 1 calorie, as you would eat it, as you would see on any of your nutritional facts, is about 4,184 joules. Some decimal points, we don't care. That's how much energy is in every single calorie that you consume. And humans are, I think, generally recommended somewhere right around 2,000 calories a day. So 2,000 times our 4,000 joules here, that's how much energy your body requires every single day to run and operate as it's recommended by health experts. So that is energy at that point, right? Power is the rate that you expend that energy. It is energy per second. So 1 watt is 1 joule per second. They mean exactly the same thing. But if we're getting away from actual terms, what they mean, thinking about these energy servants that we've got. How much does it take to actually run our day-to-day lives? And I'm going to assume, because this is recorded for my class, that the majority of you watching are Americans. And if you are an American, then on average, you're using about 10,000 watts constantly. I don't mean at peak efficiency. I don't mean somebody else that is living in a mansion that requires way too much heating and they just have no insulation. I'm talking about on average, you are constantly using 10,000 watts. And that is probably a surprising number if you're thinking about the devices surrounding you right now. I'll admit that's a pretty surprising number if I'm even me considering what I'm dealing with right now, right? If I've got my 2 light bulbs, that's 200 watts. So that's definitely not 10,000. My computer, 500 or 600 maybe. My phone, a very insignificant portion actually, only single watts. So that really doesn't contribute. So where's that 10,000 coming from? Well, there's a lot of different places. There are lights in your room, of course. There's the computer that I'm operating on. There's your vehicle. There's a hairdryer. There is a refrigerator in your grocery store keeping the food cool before you go get it. There's all of the logistics in shipping between giant cargo ships and semi-trucks on the road right now. All of those things are contributing to the energy that you, on average, use. Right? Because in some sense, on average, we all benefit from a lot of those things. You might not specifically benefit from one piece or another, but on average, all of us benefit from all of these different sources of energy, right? We've all got a little bit of a hand in the responsibility. The grocery store wouldn't exist if there weren't people there to buy things from it. So this is what we mean when we say that there are 10,000 watts that you're constantly on average using. The whole framework of the country is using this on average 10,000 watts per person. And arguably you could cut some of those things again, but we're talking about broad strokes here. So something like that, right, requires on average for you to have 100 different individual people turning those hand cranks, pushing your car, doing all of those things at once. And even more so, if you're talking about like an SUV, if you want to accelerate an SUV, you've got to borrow some energy servants from your neighbors for just a little while you speed up, because the amount of energy you require to make something like that go faster at the rate that it does is huge. That's why gasoline is such an important fuel source, because it's so energy dense. But anyways, between all of these different things, when we're considering them like this, right, there's just a lot to be used. And this is why it's very difficult to go to some sort of zero energy society, because, I mean, you can make cuts, but how many cuts can you make that are going to be significant? It takes broader changes to actually start to impact that number any more than we already do. So let me talk about some of these things as we're getting into them, and I think I'm going to finish this lecture here on the next slide or two. Joules are the common unit that we use in physics, but of course, if 1 calorie is 4,184 joules, and then we compare that to the number of people required to make a single SUV go a little bit faster, joules are not going to cut it. Joules very quickly are just not going to be a very good practical unit. We pick our units carefully most of the time. We try to pick units that are reasonable, that make sense to us, that we can conceptualize. So first, I have to introduce another unit that I do not like to use in any other context, but it's the British thermal unit. It's that old imperial system coming back again. But a British thermal unit is an old way to categorize what's going on with energy. But we don't actually even consider the BTU, the British thermal unit. Instead, we consider the quadrillion British thermal units. So it's used frequently enough that we have its own name, right? So we call this a quad. A quad is 1 quadrillion British thermal units, or 1,055 times 10 to the 15th joules. And I laugh at this, I chuckle a little bit at that number, because I can't conceptualize a number like 10 to the 15th. I've been working with numbers a long time, right? I've got my experience in this. A number that large is not something that my mind is able to wrap its head around. There's just no way. And that's why we use the unit of a quad instead. It packages that nice and neat. I can't imagine 10 to the 15th joules, but thinking about 1 quad, 2 quads, 3 quads, comparing those, I can do that. So, and there's a fun fact on this here right at the bottom, is that if you had 1 quad of energy, you could power a single LED light bulb for about 31 billion years. So it's, more than a few light bulbs are what we're running on right now. But I think this is going to be my last thing here, my last 2, how's about? So 2019, these numbers are from 2019 largely because, well, things got a little messy there for a while. So focusing on these because they were normal, typical years, the last normal-ish, typical-ish year that we've had. Global energy usage, 553 quads in total, split among 7.7 billion people. USA, single-handedly, responsible for about 100 of those. Only having, I'll keep these in the same units, 0.3 billion. So 7.7 billion used 550, 0.3 billion used 100. There's a significant portion, right? There's a reason why I'm talking about America and these things, because we've got a pretty significant energy usage. Talk about that more next time. But if you wanted to put this on a stack, a few different ways to conceptualize this, we're looking at about 100 billion barrels of crude oil to keep that energy going. Now, of course, we're not getting all of that energy from oil, but a significant portion of the oil does go to that. So imagining how many tankers it would require to transport something like that. So, anyways, I don't mean to leave this on sort of a grim thought. We'll have some other things that we dig into next time, talk about where this energy goes, how we use that. But I think for now, this is a fantastic place to end our first lecture. Next time, coming back with 1-2, we'll finish these slides out, talk a little bit more about what's going on with all of this energy that we're using. But until next time, I'll see you again.